In this video, we are going to look at energy and oscillations. So we're going to take just a couple bullet points of notes and do 2 sample problems. So as I mentioned in an earlier video, unless otherwise stated, you can assume that the total mechanical energy is conserved in oscillations. And that what that means is that kinetic and potential are kind of opposite to each other. So this diagram is kind of what I mean by that bullet point. So U, which stands for potential energy, and K, which stands for kinetic energy, the U is that orangey red line, and the K is the blue line. So when the object has maximum potential energy, its kinetic energy is at a minimum. And as the object gains more potential energy there, or more kinetic energy there, it is losing potential energy. So whatever kinetic energy does, potential energy is doing the opposite. And when potential energy is at a maximum, kinetic energy is at a minimum, and vice versa. So we can use that information to solve problems. Oh, and also, the energy, the total mechanical energy, will always equal U plus K. So it'll equal the potential energy plus the kinetic energy. So sample problem 1. A mass of 1.8 kilograms is attached to an ideal horizontal spring of constant 220 newtons per meter. The object is initially at rested equilibrium. You start the object oscillating with an amplitude 0.02 meters on a horizontal surface of negligible friction. How much work do you do to set it into oscillation? What is the speed of the object when the spring is compressed 0.01 meters? How far is the object from equilibrium when the kinetic energy of the object equals the spring potential energy? So a lot of this we should already know how to do from our unit on energy. For part A, it asks for the work. Remember that the work always equals the change in energy. In this case, you're doing work on an object that's on a spring. So you're giving that object elastic potential energy. So the work is going to equal EPE, and EPE is equal to 1/2 kx squared, and we have K and X. K is equal to 220, X is equal to 0.02. Don't forget to square it. If you plug all of that into your calculator, you should get 0.044 joules. Now, what this number here means, that's the work that had to be done to stretch it out to 0.02 meters, but this is also the maximum energy that the spring block system has, because that's the greatest it's stretched. So when it's stretched out the most, it'll have this amount of potential energy. For part B, what is the speed of the object when the spring is compressed 0.01 meter? Well, this thing is oscillating, so it's being stretched out and going back in and going in further and then going back out again. So at some point, this is going to be compressed 0.01 meter. So let's say that when it's stretched out to 0.02 meters, that's our initial scenario, and it'll go through equilibrium, it'll compress again. So our final scenario is when it's compressed to 0.01 meter. So energy is conserved, so the initial energy at position 1 has to equal the kinetic plus potential energy at position 2. So I'm going to say EPE1 equals EPE2 plus KE2. And what I'm looking for here is the speed at position 2. So now I want to go ahead and plug in formulas for my types of energy. And notice how I'm using subscripts here to make sure I know which values to plug in later. And I'm going to go ahead and cancel out all of those 1/2. K is 220, X1 is 0.02, and X2 is when it's compressed 0.01 meters. The mass of the object is 1.8, and V2 is my variable, so I'll leave that as my variable. That for V2. Subtract 0.022 from both sides. Then I'll divide both sides by 1.8 and then take the square root of both sides to get that V2 is equal to 0.19, and the units there are meters per second. So that's my answer to part B. Then part C, how far is the object from equilibrium when the kinetic energy of the object equals the spring potential energy? So by spring potential energy, they mean elastic potential energy. So again, we have that energy is conserved, and it's conserved throughout the entire motion, and we know that at one point the EPE will equal the KE. So I'm going to start just by writing that. And I'll also plug in my formulas. However, I need more information because I don't know X and I don't know V. I just know that those two are equal to each other. However, I do have some information from earlier in the problem. I know that the total mechanical energy of the system is going to be 0.044 joules. So when these two are equal to each other, both of these have to add up to 0.044. So I'm going to solve this expression for kinetic energy because I know that's what I eventually want to plug in. So and then I'll say 1/2 kx squared is equal to 0.044 minus EPE. And I know that my elastic potential energy is equal to 1/2 kx squared. And I can add this 1/2 kx squared to both sides. So I will have kx squared equals 0.044. And I want to solve this for x because, again, I want to know how far is the object from equilibrium. So I want to plug in my 220 for k. And then if I solve that for x by dividing both sides by 220 and then square rooting both sides, I will get that x is equal to 0.014 meters. So what that means is that the block is at 0.014 meters when the kinetic energy and elastic potential energy are exactly equal to each other. All right, sample problem 2 should look familiar because you may have seen this on a test. So we've got a 20-gram bullet collides with a block of mass 800 grams horizontally at a speed of 230 meters per second and becomes embedded in the block. The block is initially at rest and attached to a spring at its equilibrium length, which has a spring constant of K equals 180 newtons per meter. Simple harmonic oscillations begin once the bullet is embedded. Air resistance and friction are negligible. So we want to determine the speed of the block immediately after impact by the bullet, determine the amplitude of the resulting oscillations, compute the frequency, calculate the maximum potential energy, and calculate the speed of the block when the potential energy is at half its maximum value. So this is the kind of problem where you have to do it step by step. This kind of combines momentum, energy, and oscillatory motion, which we know how to do now. So when the bullet becomes embedded in the block, that is called an inelastic collision. Remember, when you see the word collides, you should automatically think, oh, I probably have to use momentum for this one. So for part A, we're just going to start with the equation for conservation of momentum. Now, because this is an inelastic collision, I can actually change the right side of my equation to be m1 plus m2 VF, because the bullet will be embedded in the block, so they'll be together and therefore have the same VF. So I can also get rid of this term because the initial speed of the block is 0. So I'm calling this mass 1 and that mass 2. Notice that these are in grams, so I want to convert to kilograms. I'll definitely need it to be in kilograms later when I get to energy, so I might as well do it now. So to convert to kilograms, you want to divide by 1,000. 20 divided by 1,000 would get you 0.02 kilograms, and 800 divided by 1,000 would get you 0.8 kilograms. So M1, I want to plug in 0.02. My initial speed is 230. If I do M1 plus M2, that's 0.8 plus 0.02, which will be 0.82. And I want to solve for VF. So let's determine the speed of the block immediately after the impact by the bullet. And 0.02 times 230 is 4.6. And my VF is going to end up equaling 5.61, and the units are meters per second. So that's the correct answer to part A. For part B, determine the amplitude of the resulting oscillations of the block. Well, you might think at first, oh man, I'm so new to oscillations. I don't know if I know how to do that. So the amplitude is actually the maximum amount that the spring gets stretched or compressed. So based on this diagram, the spring is going to get compressed, and it's going to get compressed due to the kinetic energy turning into elastic potential energy. So this is pretty much asking you the same thing you may have seen on a test. So it's asking you, how much does the spring get compressed? So we've got kinetic energy, which is 1/2 mv squared, turning into elastic potential energy, which is 1/2 kx squared. Gonna cancel out the 1/2. M is 0.82, because remember, it's the bullet plus the block. V is the V we just found in part A. K is 180, and we're looking for X. So you can solve that for X by dividing both sides by 180 and taking the square root of both sides, and you should get that X is equal to, if you round to 2 decimal places, 0.38 meters. So that's how much that's its amplitude, its maximum displacement from equilibrium. Okay, let's do part C. We want to compute the frequency of the resulting oscillations. So I didn't put the formulas here because I think you should know how to look them up by now. And the frequency is the inverse of the period. So on your official AP formula sheet, you should have that the period of a mass on a spring is 2 pi times the square root of m over k. So it should be 2 pi times the square root of 0.82, because that's the mass of the block plus bullet, divided by 180. Take the square root of that. Just plug that all into your calculator, and you should get that it is equal to 0.424. And remember, that's the period, which is in seconds. And to get the frequency, I just want to do the inverse of the period. So you can press that nice inverse button on your calculator, and that should be equal to 2.36. Remember, the units for frequency are hertz. So that is your answer to part C. And then part D, calculate the maximum potential energy of the system. There's actually a couple different ways we can do that. One way is to say, oh, well, the maximum kinetic energy of the system is equal to the maximum potential energy of the system because mechanical energy is conserved. Or you can just straight up calculate the potential energy of the system when it's at its maximum compression. And we found the value for maximum compression, so that's nice. So for part d, we can say that the elastic potential energy at its maximum is equal to 1/2 kx squared, where k is equal to 180, and x is what we calculated in part B. And if you plug that all into your calculator, you should get 12.996. And the units for energy are joules. For the last part of this problem, we want to calculate the speed of the block when the potential energy is at half its maximum value. So I would start this problem by just finding out what half the maximum value is. So do 12.996 divided by 2, and you should get 6.498. And we just want to set kinetic energy equal to that. So 1/2 mv squared equals 6.498. And my mass is that 0.82. And I'm just solving for v. And if you solve that for v by dividing both sides by 0.41 and then taking the square root of both sides, you'll get that v is equal to 3.98 meters per second. And this makes sense because it's less than this 5.61 here. 5.61 is the maximum speed that it has because that's the speed that it has right after it was hit. So it makes sense that if it has half the kinetic energy that it did when it was first hit, that the speed will be less. So hopefully you see that energy in oscillations is pretty much stuff that we've already covered, and you have a better idea of how to solve oscillation problems that involve energy.